We're going to talk about correlation, the first step towards figuring out relationships between two variables. In the case where we have x and y variables, we want to know if they're related. We use correlation or covariance. Note we're talking about related, not caused. We have so many instances where two variables might covary, but we cannot say that one causes the other. They might each cause the other with a circularity of causation. They might both be caused by some external factor. We often look at pairwise correlations, even though, of course, the world is not so simple, but our brains are simple. It can be useful to assess at least whether two variables tend to covary. And that measurement generally involves multiplying the two variables together, which seems surprising. Why is that? Suppose we have a simple case where x has a two-part distribution that depends on another variable y, where y is what we call a dummy. It's either 1 or 0, no other value. Dummy variables are often used to encode simple answers to like yes-no questions, where yes gets a value of 1 and a no corresponds with a 0. Dummy variables sometimes called binary or logical or Boolean. X might have a different mean depending on the value of y. Millions of different examples. GPA, the mean might depend whether the student is grad or undergrad. Now, of course, you might object, hey, there are a lot of other reasons that GPA is going to change, not just those little ones, but of course, we're not ruling out further complications, we're just working through one at a time. In a case where x has two distinct distributions, depending on whether the dummy variable y is 0 or 1, we might find the simple average for each part. Calculate the average when y is equal to 1, the average when y is equal to 0, which we denote with those vertical bars. X bar conditional on y equals 0, X bar conditional on y equal 1, or put in a subscript, X bar subscript y equals 0, X bar subscript y equals 1. Those are conditional means. They give the mean conditional on some value, in this case, the value of y. Now here, x bar conditional on y equals 1 is the same as the average of x and y multiplied together, which I've denoted as xy bar. The bar is over both, so it's the mean of the multiplication, which, spoiler alert, is not generally equal to the multiplication of the means. Xy bar is not generally equal to x bar times y bar. Now, the reason is the multiplication of x times y has a bunch of terms drop out when y equals 0, because anything multiplied by 0 becomes 0. So in this case, the mean of x times y is the mean of x conditional on y equals 1. So distinction between the unconditional mean of x and the mean of x times y gives useful information about how x and y covary. We can see how this information is valuable when y is a dummy variable. It's a little more difficult to see that it's valuable when y is continuous. Why would we want to look at the multiplied value, x times y? We're accustomed to looking at graphs that show values of two variables and trying to discern patterns. Here are two graphs of financial variables. On the left, returns of Hong Kong stock index and Singapore stock index. On the right, stock returns and interest rates. You don't have to be a highly skilled statistician to see the difference in the relationship. It seemed reasonable to state the Hong Kong and Singapore stock returns are closely linked, while stock returns are not linked to interest rates. More important for us now is to ask, how could we measure those relationships? Two graphs are on the extreme cases. How can we distinguish cases in the middle? And one farther, even more important question, how can we guard against seeing relationships where, in fact, none actually exist? That second question is the big one most of the course and discipline of statistics tries to answer. But we'll start with the first question about what to measure. Well, correlation measures how or if two variables move together. Above, we looked at the average of x times y when y was a dummy variable, taking only values of 0 or 1. Now, y is not a dummy. It's a continuous variable just like x. It's still useful to find the average of x times y, even in the case where y is a continuous value. And we take that multiplied, that's xy bar, is 1 over n times the sum of x times y. Sometimes we assume that x and y each have 0 mean, which is a simple linear transformation to make. Just subtract each mean. That makes the formulas look a little more fearsome, but isn't actually much of a change. And generally when we have these discussions, we want to answer questions such as, when x is big, would we also expect that y is big? But we have to refine the question. The word big changes meaning depending on context. We often refine that to be, when x is above its mean, would we expect y to also be above its mean? Then the average of the multiplied values is called the covariance, sometimes denoted as sigma xy. A positive covariance shows that when x is above its mean, y tends to also to be above its mean, and vice versa. So positive number times a positive number gives a positive, or a negative number times a negative gives a positive. On the other hand, a negative covariance shows that when x is above its mean, y tends to be below its mean, and vice versa. So when one is positive, the other is negative, which gives a negative value when multiplied. Covariance is sometimes scaled by the standard deviations of x and y in order to eliminate problems of measurement units. So the correlation is sigma xy divided by sigma x times sigma y, sometimes denoted rho. With some algebra, you can show that rho is always between -1 and +1. Two variables will have a perfect correlation if they're identical or differ only by a linear transformation. They'd be perfectly inversely correlated if one is just the negative of the other. Variables with a correlation close to 1 in absolute value are very similar. Variables with a low or 0 correlation are nearly or completely unrelated. Now we'll return to this point, but remember that a negative correlation means the variables are related. A surly teenager who always does exactly the opposite of what they're told, that's not independent. Their actions are correlated with the advice given, just in the opposite direction. Just as with average and standard deviation, we can estimate the covariance and correlation between any two variables. And just as with sample average, sample covariance, and correlation, we have distributions around their true values. For a case where the two variables almost form a line with a positive slope, we can't just say that one is big, the other is 2. We want to be a little more precise. When one is above its mean, the other tend to be above its mean too. Might additionally state that when the standardized value of one is high, the other standardized value is also high. The population correlation between x and y, rho xy, sample correlation is r xy. Again, the difference is whether you divide by n or n minus 1. Both correlations are always going to be between -1 and +1 though. We can often think of drawing lines to summarize relationships. Correlation tells something about how well a line would fit the data. A correlation near 1 tells there's a high relationship, 1 in absolute value. Correlation needs 0 is 0 relationship. You might commonly see a covariance matrix if you're working with many variables. The matrix shows the covariance or correlation between each pair. So if you have 4 variables with unimaginative names x1, x2, x3, x4, then the covariance matrix might look something like that. The matrix is lower triangular because covariance of x with y is the same as covariance of y with x. Return to the formulas if you're not convinced multiplication is symmetric. So we know the upper entries would just be equal to their symmetric lower triangular entries. So I left the upper triangle blank. And we can also show, again, a bit of math, that covariance of x with x is the variance of x. So the entries on the main diagonal are the variances. If we have a lot of variables, I don't know, 15, 20 or more, then the covariance matrix can be an important way to easily show which ones are tightly related and which ones are not. As a practical matter, sometimes perfect or very high correlations can be understood simply by definition. A survey asking, do you live in the city? Do you live in the countryside? We'll get a very high negative correlation between those two questions. Other correlations can be caused by the method of sampling. But we will come back Or go further, asking some questions. When we calculate a covariance or correlation, what number is big? Of course, we'll see random errors, but what amount of evidence can convince us that there's really an important correlation? When we calculate conditional means or find differences between groups, what difference is big? What amount of evidence would convince us there's a difference? In any research question, we get a variety of answers. We try to separate out the signal from the noise. We need to think about randomness. In other perceptual problems, what we call noise or blur.